This is Jessica Dunn, and we are going to be looking at mixed streams of cash flows in this discussion. Annuities are equal periodic cash flows. They occur over a specific period of time. They may be inflows or outflows. So to qualify for an annuity, there are 3 items that must suffice. The cash flows must be equal, they must be periodic, and they must be finite. So it must be the same equal amount. It must occur over the same time intervals, periodic, and it must be finite. So there has to be an ending point. It can't occur forever. So there are 2 different types of annuities. There are ordinary annuities and there are annuities due. An ordinary annuity is an annuity where the cash flow occurs at the end of the period, and an annuity due is a cash flow that occurs at the beginning of a period. So there are 2 good examples. An ordinary annuity would be something like your mortgage. You go to the bank, you get a loan, you purchase your house. Your first payment isn't due for 30 days. So your payment is due at the end of the period. An annuity due, an example would be your rent. So if you are renting an apartment, usually your landlord is going to require a deposit and your first month's rent upon signing. So you're paying for that, the use of that house at the beginning of the period. The primary difference is that an annuity due is always larger than an ordinary annuity because you have extra compounding time. So if your rent is due on the 1st, as opposed to your mortgage being due on the 31st, that landlord has an extra 30 days there with which he can earn interest. So let's look at an example. Fran is choosing between 2 annuities. Both are 5-year. Both pay $1,000 per year. Annuity A is an ordinary annuity, and Annuity B is an annuity due. So the only difference is that with Annuity A, the payment is occurring at the end of the year, so December 31st. With Annuity B, it's an annuity due, so you're receiving that $1,000 at the beginning of the year or January 1st. So the 365-day difference between the payments, and so you're having less time for that money to grow. So you're losing one compounding period with an annuity, an ordinary annuity, as opposed to an annuity due. So you can calculate the future value of an ordinary annuity by using this equation. The future value is equal to the cash flow or the payment. Remember, we have that payment button times 1 plus the interest rate raised to the number of periods minus 1 divided by the interest rate. So the computations are becoming more complicated. And so with this, I highly encourage you to get very comfortable with your financial calculator as to avoid excess time. So let's do an example. So Fran wants to know how much money she will have at the end of 5 years if she chooses Annuity A and earns 7% annually. So if she receives $1,000 every year, puts it into a savings account that earns 7%, how much would she have at the end of the 5 years? So let's draw this out on a timeline. So as of today, she is not receiving anything. She will be receiving $1,000 every year for 5 years. Remember the qualifications for an annuity? It's equal, it's periodic, and it's finite, which this qualifies for all of those. $1,000, equal amounts, periodic, every year, finite, only 5 years. So because it qualifies as an annuity, we can use the payment function on our financial calculators. So she's going to receive this $1,000 every 5 years, and she wants to know how much is all of these worth if I continue to reinvest them. How much will I have at the end of 5 years? So let's put this into our financial calculators. Our financial calculators have the inputs of future value, present value, N, IY, and payment. Let's start with the easy ones. We know that it's 5 years. We know that it earns 7%. We also know that she has nothing as of right now, so she hasn't received anything yet. We want to know how much she will have at the end of 5 years. And the payment is that equal periodic finite cash flow of 1,000. So the payment button just allows you to not have to find the future value of $1,000 5 different times. So it's telling your calculator that this $1,000 occurs every year beginning one period from now and lasts until year 5. So let's solve. Using our financial calculator, we can put in what we know. So first step, clear our time value of money. We have 5 years at 7%. We've received nothing as of yet. And we're going to receive $1,000 every year for 5 years. We want to know how much that would be worth in aggregate at the end of the 5th year. So this is an example of how the negatives and positives can be purely there for interpretation. So we see that we get a negative $5,750.74. If instead you had interpreted this as, well, she's going to receive $1,000, but she's going to immediately put that into a savings account, so she's not actually touching it, she's actually receiving it, putting it into an account, so that's money going out of her pocket, then you would have gotten a positive 5,750. Let me illustrate. So let me just replace that negative with a positive 1,000 and compute our future value. Sorry, replace that positive with a negative and compute our future value. And now we have a positive $5,750.74. So it's purely interpretation at this point. So it just depends on how you interpreted the problem. Either way, when you answer this, there is no such thing as something costing or having in your account a negative $5,750.74 if we're talking about a savings account. So in ordinary annuity, we can also find the present value of that. So with the ordinary annuity, the formula says that the present value is equal to the cash flow or the payment divided by the rate times 1 minus 1 divided by 1 plus the interest rate raised to the number of periods. So you can see that the computations are becoming more complicated. Let's do an example. Braden Company wants to determine the most it should pay to purchase an annuity. The annuity consists of cash flows of $700 at the end of each year for 5 years. So at the end of each year tells us that this is an ordinary annuity. So they could have said it either way. Now with an ordinary annuity, it occurs at the end of the period. So the key thing here is that you have to make sure that your calculator is in end mode. Your calculator is usually in end mode, so it doesn't require anything that you have to do. We're going to get into situations where it needs to be in begin mode in just a few minutes. So you're receiving $700 at the end of each year for 5 years, and the required return is 8%. Let's just put this on a timeline. So today, we're wanting to know how much should we pay for this annuity. And you're going to receive $700 every year. Now that $700 should be a positive because you are going to receive that $700. So let's put in what we know. We know that N is 5. Our rate is 8%. Our payment, equal, periodic, and finite, is $700. We're wanting to solve for present value, and our future value is 0. Now this is where some students get confused, is whenever I say that the future value is 0, they say, oh wait, look, in year 5 there's a $700 cash flow. This payment encompasses a single cash flow, or an equal cash flow, for every single period, years 1 through 8 in this, or 1 through 5 in this instance. So by saying that there's a payment of 700, that tells your calculator that 700 will occur in year 1, 2, 3, 4, and 5, because you put in 5 years here. I know that the future value is 0 because you're receiving 700 here and nothing else. So you're receiving nothing in addition to that 700. So if you can say that Braden Company is going to receive $700 every year and nothing else in the final year, then your future value is 0. So let's work this out on our financial calculators. First, clear your time value of money to set all of your fields equal to 0. Now let's put in what we know. Start with the easy stuff. We know that this is 5 years. We know that their required return is 8%, so they must earn at least 8% on investments. We know that their payment is 700 because that is the recurring cash flow that is equal, periodic, and finite. And our future value is 0 because they're receiving nothing in addition to that 700 in the 5th year. So let's solve for compute present value. You get a negative $2,794.90. That makes sense because Braden Company wants to determine what is the most they should pay. So we're wanting to determine what would be our cash outflow to purchase this cash inflow. So in sentence form, we would say they'd be willing to pay $2,794.90 to purchase this annuity that earns them $700 a year for 5 years. If they paid less than $2,794.90, then they would be earning more than 8%, which they would be happy about, and they would proceed with the transaction. So they'd be willing to pay up to. Okay, so now let's look at annuity dues. So these previous calculations were about ordinary annuities where our calculator was in end mode, which is something that we naturally have. We always have our calculator in end mode for normal calculations. But now let's look at an annuity due. Remember, the only difference between an ordinary annuity and an annuity due is that the cash flow occurs at the beginning of the period with an annuity due. So here's the formula. It's getting very, very complicated. So let's redo that same problem we did. But now let's say that Fran is choosing annuity B, that ordinary annuity. So remember, she's receiving $1,000 a year for 5 years, which she puts into a savings account, doesn't touch. She wants to know how much she would have at the end of the 5th year. So let's put this on a timeline. And your timeline is going to look exactly the same as it did for the previous problem. By switching your calculator to begin mode, it takes care of all of the placements of the cash flows, so you don't have to worry about that. So she's putting $1,000 a month into a savings account, or $1,000 a year into a savings account. How much would she have at the end of the 5th year? So remember that she could earn 7%. Okay, so the first step is you have to put your calculator in begin mode. And so I typed it out here, exactly the keystrokes that you have to make. Second payment, second enter, second quit. So let's do that together. To put our calculator in begin mode, it's not quite so much that you have to memorize all of this, because do remember that it says BGN right here above payment. Above your payment button, it says BGN. So we know we're trying to access that. So to access that, we have to push second payment because begin is written right there. Now your calculator prompts you. It says, okay, it's in end mode. To change that, we have to push set. Second enter allows us to access the set button. Now we can push clear or quit or whatever. Second quit. Now we know that our calculator is in begin mode because it says BGN in the upper right hand corner. So this is the same problem we did before, except now we're working it with our calculator in begin mode. So here she has an investment for 5 years. She earned 7%. She has nothing in her account today. She's putting $1,000 each year into a savings account, and we want to know how much she will have. The future value, $6,153.29, which is more than she would earn if she had put the money in at the end of the year. She's basically getting an extra interest payment because instead of putting it in on January or December 31st, she's putting it in 365 days before that on January 1st, 364 days, whatever. And so she gets a greater amount because she has longer for her money to grow. So before, when we worked this problem out as an ordinary annuity, we had found that she would have $5,750.74. And now she has earned $6,153.29. So she has more money because she has given her money a longer amount of time to grow. But the problems are worked the same way. So the first thing that we need to do whenever we're working an annuity problem, specifically an annuity due problem, is that as soon as we're done with the problem, we put our calculator back in end mode, because we never have our calculator in begin mode unless we're working an annuity due problem, and it will mess up your calculations. So let's do that together. My calculator is in begin mode. I want to put it in end mode. I want to take it out of begin. So second, payment, second, set, then clear. So it's the exact same process backwards. We can also calculate the present value of an annuity due. Again, the equation gets increasingly complicated. But let's just jump into an example. It's the same example as before, except now our cash flows occur at the beginning of the period. So instead of coming out and saying that this is an annuity due problem, it says that the cash flow occurs at the beginning. So you do have to recognize that this is an annuity due. An annuity due simply means put your calculator in begin mode. So Braden wants to determine what is the most it should pay to purchase an annuity. The annuity consists of cash flows of $700 at the beginning of each year for 5 years, and the required return is 8%. So let's put this on a timeline. And our timeline is going to look the same because our calculator manages the placement of the cash flows within the year for us using the begin mode. 700 is going to be received every year for 5 years. We want to know how much should we pay for that today. That's a 7. So 5 years, 8%. Our payment is $700. Our future value is 0 because, again, we're going to receive $700 every year for 5 years and nothing in addition to that. So our future value is 0. So let's work it out on our calculator. The first thing we have to do is put our calculator in begin mode. So second payment, second set, clear. Now we see that it's in begin mode. Let's clear our time value of money. So we have 5 years at 8%, $700 received every year for 5 years, and nothing else. So let's compute the present value. We have $3,018.49. Notice that we're willing to pay more for the annuity due than we were willing to pay for the ordinary annuity. So we're willing to pay up to $3,018.49. With the ordinary annuity, we were only willing to pay $2,794.90. We're willing to pay more for this because we are receiving these cash flows sooner. We would receive them at the beginning of the year as opposed to the end of the year. So we would have extra time for that money to grow. A perpetuity is similar to an annuity, except we're removing some of the constraints. So remember, the qualifications for annuities are that the payments must be equal, periodic, and finite. What if we remove the restriction of finite? What if we make these payments infinite? So the qualifications for a perpetuity are the cash flows must be equal, periodic, and infinite. So all three must hold. So a perpetuity is an annuity with an infinite life. So it makes the same exact dollar amount cash flow at the same period in time each year, or each period, or each month. And here is the formula for solving for this. Now with the perpetuity, there is not a function in your calculator to solve for perpetuities. You have to use a formula. So there's only two examples, two times in this chapter where you will have to use formulas, and this is one of them. So you do have to remember this formula. Your present value is equal to your cash flow or your payment, however you want to think about it, divided by your discount rate. And remember here that we are not using the time value of money formulas that are programmed into your financial calculator. And so here, this rate is a decimal point interest rate. So let's do an example. Ross wants to endow a chair of finance at his alma mater. The university indicated that it requires $200,000 per year to support the chair. The endowment earns 10% per year. So how much must he give so that the university could withdraw $200,000 a year forever and never touch the principal? So we put this on a timeline. You might be able to see it better. So we're wanting to know how much should he donate to the university today so that every year they can withdraw $200,000 forever. So we have to recognize this is a perpetuity because it is infinite, and we use the formula for solving for the present value. The equal recurring cash flow is $200,000. We divide that by our discount rate of 10%, and we get $2 million. So if he were to donate $2 million to the university, they would be able to withdraw $200,000 a year in interest and never touch that $2 million donation.